So in the previous subsection, we defined formally what the central limit theorem is. But we also said that the general kind of principle behind the central limit theorem is that the combined effect of lots of small effects as a totality is approximated by a normal distribution. So of course, the particular case we saw was that if you add up IID random variables and then normalize appropriately, you get a normal distribution. But we can also use this in a slightly more hand-wavy sort of way to allow ourselves to approximate other distributions by normal distributions. So some of these will be obvious why they're true, and some of these you'll kind of have to take my words for it. But here are some things that can be approximated by normal distributions. So if you've got a binomial NP, and if n is large and p not too small or too large, then you can approximate this binomial by a normal distribution. In particular, it's n. We know that its mean is np, and we know that its variance is np1 minus p, because those are the expectation and variance of a binomial distribution. I say p not too small or too large because we know, of course, that when p is small, we're better off approximating by a Poisson NP. So if p is very small, you're probably better off with a Poisson. If p is very big, well, there's a question about that on the problem sheet, and think about what sort of symmetry arguments might be able to tell you about what to do when p is really big, given that we already know what to do when p is really small. If we have a Poisson lambda and lambda is big, then that can be approximated by a normal distribution. We know that the expectation of a Poisson lambda is lambda, and we know that the variance is lambda as well. So that would be approximately n lambda lambda. If we add up a bunch of geometric distributions, add up n IID geometric p's, again, p not too close to 1. That distribution, incidentally, has a name. Some people call it the negative binomial. But again, this thing is roughly normally distributed. The expectation of geometric p is 1 over p. So if we add up a bunch of them, we'll get n over p. Similarly, we know that the variance of this is, of one of them is p over 1 minus p squared. So of n IID ones, we'll get n that. And then similarly, if we add up n IID exponential lambdas, this is sometimes called a gamma distribution for what it's worth. This will be approximately normal. The expectation of one of those is 1 over lambda, so n of them is n over lambda. The variance of one of them is 1 over lambda squared, so n of them is n over lambda squared. I haven't put normal down here because we know that the sum of normal distributions is exactly a normal distribution. No approximations needed. Add up normal distributions, yeah, a normal distribution. So I thought we'd give an example of how to do this. So suppose I toss 1,000 coins. What's the probability I get between 495 and 505 coins? So we know that on average we expect half of them to be, sorry, heads, not coins. We know on average we expect 500 of them to be heads. So it seems like there might be a pretty good, that would be very close to 500. So what's the chance we get between 495 and 505? So note this is saying that if x is binomial 1,000, half, asking for the probability 495 is less than or equal to x. So obviously, if you've got r, you can calculate this exactly. And in the notes, I show you what commands I used in R. But it turns out the answer is exactly 0.2 0.720. So, a little bit more than a quarter chance of getting, very close to 500 heads and 500 tails. But we could approximate this binomial by a normal distribution, which is that we could say it's approximately normal. So the expectation is 1,000 times a half is 500, and the variance is 250. 1,000 times a half times 1 minus a half. So if we took that approximation, we could call that thing y, the approximation. Then what would we get from this approximation? So we'd be saying that the probability 495 is less than 505. It is approximately probability that 495 is less than or equal to y, our normal approximation, is less than 505. So obviously you could calculate, you could do some standardization and look it up in your statistical tables. I just did it in R. You can see the commands I used in the notes to calculate this in R. And I got 0.2482. So, it's not a bad approximation. 27%, 25%, only it's a few percent out, right? 2% out of something that's about 25%. That's like almost 10% out. So it's an okay approximation. It's getting us in the right ballpark, but it's not like super accurate. But there is something we can do here, in fact, to get a better approximation. This is the fact that our binomial, the thing we started with, was discrete. It could only take integer values, 494, 495, 496. Whereas the thing we approximated it by, the normal distribution, well, that was continuous. So that could take anything between 494 gradually through to 495, gradually through to 496. So when you're doing this, it can be beneficial to use what's known as a continuity correction, which is to allow for the fact that when you say that the binomial is equal to 495, that means you haven't jumped down to 494. And when you said it was 505, you mean it hadn't jumped up to 506. But the normal can gradually go from 495 down to 494 and can gradually go from 505 to 506. So actually, you might get a better approximation if you allowed yourself to go like halfway out to the next discrete point. So if you said that, well, maybe 494.5, that's like halfway between the 495 and the 494, that the binomial couldn't do it, had to suddenly jump. But if you're going gradually, then maybe you should already go halfway there. Similarly, at this stage, we should go halfway up to the next thing. So there and there, we are go halfway to next discrete point. Obviously, the discrete points are normally integers. That's what most of our discrete random variables have. But if you have some weird discrete random variable that takes unusual values in its range, then you still might want to go halfway outwards towards whatever the next discrete point is. So if we try with this continuity correction, again, you can look up the normal distribution things either in a table or using R, the commands I used in R in the notes. This time, with the continuity correction, we get 0.2720. Well, that agrees exactly with that exact solution. We're correct to 4 decimal places. In fact, if you look at the next decimal place, I think the exact answer gives a 3 as the next decimal place, and that gives a 4. But we're really, extremely close there. So when approximating a discrete binomial, you can often get better, more accurate answers by using a continuity correction like that. And the accuracy of that answer shows how useful normal approximations to other distributions can be.